Okay. Okay, so our next speaker is Craig, who's traveled up from Cambridge this morning to speak to us. Over to you.
Oh. I do.
Oh,
We discovered that.
I was holding the microphone.
This is why we have lanyards.
We asked Julian never to pick up.
yeah. I'll listen in.
Okay. I am Craig. I work at Quantinuum, based in Cambridge. We make, not personally, but we make quantum computers and do lots of research into how to use them. I'm going to be talking about BRAT, which is my project, which is a functional programming language to ease the lives of people who are writing these experiments using quantum computers, and it's in collaboration with all these lovely people. First, quantum computing in a nutshell. The typical process that we do when we're running an experiment is we come up with some circuits and then we send them to the computer. Everything is very hardware as a service, where there's much more demand than usable quantum computers out there. So we run it many times and then we get back a bunch of bit strings, which we process and learn something about how we should fix our circuit to start again, or whatever it was we were investigating in the first place. The online part is very expensive, so we would like to avoid having any runtime errors. At the moment, most frameworks for writing circuits are written in Python, which is stresses me out a little bit. So you don't need to remember this strictly, but this is how the circuits that we're building up look. We have space on the vertical axis, where these are qubits, and there's a fixed number of them, which we want to control whether people exceed the budget of qubits that actually exist on the machine. And it's something that I don't worry about so much, is that the more gates you put in your circuits, the more you're eroding the fidelity of your qubits. So if you write something that takes a long time to run, eventually you'll end up with just noise. So there's a lot of work into reducing the amount of gates based on identities that we've been researching. Yeah, as I said, at the end, we measure all the qubits and we get back a bit string. We assume everything starts in the 0 state and everything in the middle is weird. You don't have to remember this, but when I say everything's weird, you've probably heard that in quantum computing, the bits are in a superposition of the 0 state and the 1 states, which isn't as important to my talk as the fact that when we have qubits up and down on the left here, the way that they're acting, this is the state space of 1 qubit. It can be anywhere such that a squared plus b squared is 1. But when we put them next to each other, we're making a tensor product of the state space. And yeah, there are some famous theorems which we have to respect when we're building the circuits. You can't clone an arbitrary state, and you can't delete an arbitrary state. I'll come back to that. And it's further to what I just said, this is how we're evolving quantum states with operators like the H gate that was in the circuit before. And when you have a tensored state space of multiple qubits and you perform an operator on both of them, you can't necessarily separate them back out again as if you were just working with a Cartesian product of qubits. So in our programs, we're dealing with 2 different worlds at once. The quantum world, where everything is linear, there's no cloning and no deletion. We have monoidal structure in terms of the tensor product, but we can't always separate it out. and we're resource constrained in that we have a fixed number of qubits that we can address. And then we have the happy land, the classical part of our program, which is generating circuits and processing data, where we can throw away and copy stuff. We can make pairs and separate them, and resources are abundant. BRAT is seeking to unite both of these disciplines, enforcing the constraints of the left-hand side and making it clear which is which when you're writing your program. And it's, yeah, as I said, the way things go is you start off in the classical world making circuits, send them away, get data which you process. The much bigger part of the picture is the classical world. And then if you're just sending out to the quantum, this can repeat in a loop for a long time until you get any results. When I said no deletion is one of the big theorems of quantum computing, there has been a development recently in that you can't make a gate which arbitrarily deletes a quantum state, but you can take the thing that you were talking about and throw it away and replace it with a fresh qubit if your device is advanced enough. So we're targeting our own devices which have this capability to just throw things away and start over. So this is device dependent. If you're doing some measure and reinstantiating, then it won't work on lots of current generation devices. But this means that we can deal with bits within circuits and do some branching based on the results of measurements. This is a bit of what BRAT looks like. There are the two worlds I alluded to. These function types look very similar, except here's a lollipop from linear logic, meaning that you can't throw one of these away. And it's a classical arrow from functional programming. So if you run both these through the BRAT type checker, you'll get an error in the top one because we tried to throw away B. And on the first one, there's no problem because it's classical data. Likewise, for trying to arbitrarily copy qubits, this is a completely trivial example, but when you're writing lots of linear typed examples, it's really easy to get it wrong. If you run this through the type checker, then you'll say you can't make a copy of Q because it's already been used in the first sites. So I should explain the notation a little bit here. This is how circuit declarations look like. We take in a row of inputs in a classic way, and this is the same way functions are invoked. And then on the outputs, we're also producing a row. The idea being that we can easily compose this. If we have a row of types of the same types, we can compose this with itself and compose functions all over. When we have quantum gates, there's a lot of qubit to qubit or pair of qubit to pair of qubit in the types. So we're aiming for easy compositions of these things. We're building up circuits from smaller parts. And a note here that this is syntactic sugar, because since the classical world is the bigger part, we're saying all of the top level declarations are classical things. So this quantum function desugars to the thunk type, which is a classical type of the function from a row of 2 qubits to a row of 2 qubits. And we have different worlds of types where the function type, it was a classical type, and the qubit type you can't use in classical programs, only when you're writing kernels. So this is repeated here in the definition, where we're writing the classical thunk, and it goes between curly braces, and then inside we have our quantum circuit, and we're just applying a bunch of gates, which looks a lot like a rotated version of what we had in the previous circuit diagram. We have qubits coming in the top, and then we're applying a bunch of gates, single and 2 qubit gates. So this is also a commonly used way of representing circuits, not as much as the first one, but when we're reasoning with them as monoidal categories, then we have composing vertically, which is what the semicolon is doing here. It's composing functions, feeding their outputs into the inputs of the previous thing. And we're composing horizontally in the state space, the tensored state space of the qubits. So when we're type checking this, the semicolon is binding more strongly. So we first check that this H comma ID applies to two things, and whatever two things we get out, we're feeding into the TID thing, and then we're feeding that into the CX, and so on. Yeah, and the way that this works is we consume it. We consume inputs until we get to the end of the row, and if we didn't get to the end of the row, then we complain. Right, so I want to work through a little example here. This is an algorithm from the literature for magic state distillation, which is to say, we want to create one of these magic states. We have a bunch of approximations that we made very cheaply, and we want to try and put those all together to make one with better fidelity than we would have had from our rough approximation. So you can prepare as many noisy states as you want. Then we have a decoder circuit, which is kind of abusing a notion from error correction, which is to say, imagine that these are all trying to encode some fault tolerant state, now try and fix the error in it. And then we will get out one good state, hopefully, and the rest of these qubits, we will measure them all and look at all of them. If everything is zero, think zero, then we know that we succeeded in making this state. Otherwise, we want to start again. Did that say something about zeros? Can't remember if it's 0 or 1. But yeah, we'll measure this syndrome, and that will feed into our decision to reset this qubit and go back and start the whole process again, or to say that we've got our magic state and we can use it for whatever we want. So this is also kind of a recent development in terms of runtime systems of quantum computers, that you can go back and write a looping thing. But it would be much nicer if we could do termination checking on those programs. So this is an expansion of the program from a couple of slides ago. So I don't need to say too much, except that we're making this diagram. This is the decoder in the middle, so it's taking their noisy states as inputs. Here there's 5, and as we're creating one output state and 4 qubits, which can be measured to say whether they think that it works or not. And this is just more of the semicolon comma thing we saw earlier, with the innovation of these operators, which are for easily converting between vectors of fixed width and rows. So we're taking a vector of length 5, and then we're exploding it out into 5 things and then collecting it at the end. Yeah. So there's a hint of this here. What's going on with the vectors? This is like, there is a value in the type. This is something from the dependently typed programming introduction. So the classical world, we have slightly more interesting types than in the quantum world. Vector of qubits, it's all quantum, but then we're taking a classical parameter, which can come from a parent function or from a top level value like 5. And it's a little example of this is we're using our small amount of dependent types to do polymorphism. So you can take in a type parameter x and then produce a function from x to x. Not very exciting. But there's a separate type parameter for the types that are in the quantum world. And then we can use this to create an arbitrary identity function for any quantum type and replace the QID that was all over the previous slides. And then this lets us write some more interesting functional programs for building up our circuits rather than just putting gates next to each other. So this is a kind of ugly version of map. We're taking in our two quantum types, a function from x to y, and it's a length, and then we're making something that acts on vectors of those lengths of x's and y's. And the key thing to note here is that we're producing a thunk of the quantum circuit, but this is a classical function that's producing the quantum circuit. So when we're looking at n here, checking that it's 0 or successor, we're guaranteeing that this is not a discriminating match when we pattern match. We've decided that since we match on 0, then this must be a vector of 0 length. So we're not allowing discrimination to happen in the circuits themselves because that could lead to runtime errors that we don't want to pay for down the line. And then if we look at n and it's a successor, then we know that the vector that we're acting on must be a cons or something of length n plus 1. And then there's classic map definition. Yeah, so we can swap this around a little bit and use our map, make it slightly nicer. Then more funky classical program. We can fold if we can provide a kernel from two things to one thing. If we can provide a kernel that makes a fresh thing, then we can fold over a vector to get one thing. This is kind of suspect because it won't work on anything that's linear, but it is allowed to work on bits. So we have two different worlds of classical and quantum programs. We have the classical Boolean and the bits of the kernel worlds. Using this, we have a helper function that we can use to check that everything we get out the end of our decoder is 0. Yeah, so that's what's happening here. We're going to stick this. I'll rewind a little bit. So we've done the decoder. That was a big lump of gates next to each other, not very interesting. And now we're looking towards this measure syndrome where we have n plus 1 qubits. One of them is our state, and 4 of them are information about whether it's good or not. So we're just going to have this measure all function, which we're doing on the n qubits, and the plus 1 we're going to call the identity on. Oh, is that a bug? I think it should be measure all comma ID, because we're measuring the n qubits and then calling any on them, and it's passing through the other thing. Yikes. So one last diversion, I think. When I talked about throwing away qubits and putting fresh things in their place, this isn't done implicitly, as you saw, because if you try and forget about a variable in a program, then we're going to shout at you. But you can call a measure function, which instead of throwing the qubit away, returns a concept of money, which is a little bit idiosyncratic, but harking back to some work by Martin Hoffman, where money is the whole left by the qubit that you just deleted. So we have a fixed number of qubits in the system. You can get rid of one of them, and that gives you one token you can use to instantiate a qubit. So the total of qubits and money in the circuit is always a constant. And this is how we go back and forth between them. of course, you get a row of the money and the bit that says the result of your measurements. So with this, we should be just about there. Preparing our noisy states isn't super interesting. We're just doing some weird gates, and we're creating a fresh qubit and ending some weird gates. So we have prepare noisy for 1 qubit, which says instantiate the money that we have, and then change the states, and we can call the map function that we defined to map that over n qubits to scale up our algorithm. And this is an illustration of the way that we're splicing thunks into place. We have our classical functions, ry and rz, and everything in here is our kernel. So purple box is a quantum function, and it's the evaluation of this classical func. We're taking the curly braces off and looking what's inside, and then we're chaining that into our pipeline here. Yeah. And also, so these are classical parameters feeding into these things, pi and pi over 4. So you can do some arbitrary classical computation out here and then feed it into the circuit if you're doing it before you start running the circuit. Okay, now the top level function should be pretty easy, but there's a little bit of awkwardness here. If we assume that the top level type signature for the function is that we have 5 money tokens and we're creating 1 state and 4 money tokens, which is to say that we're going to repeat until we actually get the state we want and give the 4 holes that we made by measuring everything. Then it's pretty simple. We just take this bit and look at it, which is the result of doing any on the list of measurement results. And yeah, we're just going to, if everything together isn't what we want, then we're going to measure the target qubits, and then we just have meaningless money, which we pass into the still again, start the whole process over. So that gives the whole state of the thing. And the shape of this, we've written it so that we can pick any n for the number of qubits in, and then this thing is going to be, this is also, okay, we can pick any n plus 1 for the qubits in, and we'll get n syndromes out in 1 state. However, the decoder is something that is kind of made bespokely. You have to pick 1 decoder from the literature, so we can't quite make this fully generic. Yeah, and then this is the body of the function. This just putting all the different parts together. We have some money, we make some noisy states, we run the decoder, we're doing uncons, it's a bit of a hack, passing 1 thing through, and the rest we're measuring the syndrome, giving back some money and a bit to say whether we should, whether we're done or whether we should keep going. That should be it for the example. There are things going on that I didn't talk about. The way that we wrote the diagram with all the explicit swaps isn't strictly necessary. We have syntactic sugar for that, like things for passing all the wires that remain in the row through and for dragging a specific wire to the front. Yeah, we have LSP mode for interactive programming, which for interactive type checking now, I should say, and a bit of an arithmetic language, which is kind of interesting for the numbers that we have in types. And this is a work in progress at the moment. So we're working on compilation via this internal IR that we're developing at Quantinuum, which is open source at this URL. That's what I'm working on right now. to be able to start running these things in anger and getting other people to do it and hearing their problems. There's also lots of quality of life things that we can do, like user-defined data types and lots of things for accessing things within the row, which is what this is about, but I don't think I have time to explain it. So that's all for me.
Nice talk. I just are you limited in the number of qubits you can work with?
I mean, yeah, it's like resources are always finite, but they're much more finite on our current state of quantum computers. For example, the ones that we're developing at the moment at Quantinuum are number of qubits in the 30s or 50s, and they get used up quick when you start planning out the things that you want to do with them.
Sorry, I mean in the type system.
Oh, sorry.
At the type level, does your kind of compilation take longer the more qubits you have at the type level?
Does your compilation take longer the more qubits you have at the type level? I mean, there's more type checking to do, the more the things that you're acting on, for sure. But not in any surprising way, slow way, I don't think.
One of my interests is type error diagnosis. And I saw some of your error messages and they looked fine. But do you have any issues with type error diagnosis when people make mistakes either in the normal Haskell part, but also in the linearity? Or is it because you're actually missing type inference? Is that related to that you don't invent types?
I mean, we are not spending as much time thinking about good error messages as we probably should be. There's usually it's classic things of somewhere we didn't do enough evaluation on types, and then when we check them for equality, something went wrong. But that's well, that's my experience debugging the compiler rather than actually writing circuits. So the linearity error messages are pretty straightforward. We don't have good. I don't know what the story is for everything else. It's quite ad hoc as we go.
Okay.
Yeah, maybe I missed it earlier, but is this a wholly on its own compiler with its wholly on its own language?
Yeah.
I was wondering then, is there a particular reason you didn't go for an embedded DSL in, say, a language that already had linear types? Was it just that it didn't map nicely, or that pulling in GHC is just a big undertaking?
I don't have a good answer. At the time when we were starting, there didn't seem to be a good option for embedding in a language with linear types. Like Idris 2 was taking its first baby steps, for example. And I guess there's Granule as well, but I'm not very familiar with what the process for embedding languages in that is.
Thanks.
So was the syntax for the gates a deliberate choice to dissuade people from using it and use more functional? Because like the diagrams remind me very much of like arrows, and that there's like this concept of arrows and the arrow syntax and the sugars to the swaps and things like that. And definitely, well, if you're not familiar with arrow, then definitely the people that were on the title slide should be familiar with arrows and its syntax.
Familiar enough. I mean, the idea of the circuit syntax is just that you have the same experience whether you're writing classical functions or circuits, and you can treat your circuits as functional programs built up from smaller parts. Usually, the distinction between these two things is your classical function is a Python program, and it's your quantum thing your quantum circuit is a Python object that you have built up the IR using Python by saying add gate, add gate. So it's to provide a nicer, more consistent experience.
Right.
Thank you very much, Craig. Let's move on to the next presentation. So thanks again, Craig.